Alright, hell yeah. So we got material mechanics, and I have a hard time just getting to it. You know what I mean? Just friggin' A, just writing down the equations and getting some idea of what's going on. So these are the equations that I write. Strength is force over area. Stretch is change in length over length. Obviously this is stress, but it's cool to say strength. This is strain. But you see how the sound almost identical, but this is stretch. This is your change in length. And then we have what relates them. It's strength is EE. Put the E's however the hell you want. But this is the constant. This is the modulus of elasticity. It relates the two because it says, hey, this normal number is equal to, hey, this tiny number of strain or change in length by some sort of proportionality constant. And to get a tiny number to equal a normal number, well, this E has to be fairly friggin' big. Okay, that's it. So let's do it. So right off the bat, they give you kind of the strength of 5,000 times 10 to the 6 pascals, or Newton per meter squared, 500 megapascals. They give you the area of 48, but we got to divide this by 10 to the 6 to get meters squared. And then we have the modulus of elasticity of 160 times 10 to the 9 newtons per meter squared. So what we can do is we can just throw, what do we know? We know area and we know strength, so we could find force. That's the first one. So let's rearrange this equation to kind of find, you could call this max force, or you could just call it yield force. You know what I mean? It's kind of nice to use kind of like max or braking, so you could do force brake, even though technically it's not when it breaks, but potentially that's when people could lose their lives for sure. But anyway, so we rearrange this equation, so we have yield strength times area, and we can just go for it. We can do 500 times 10 to the 6 newtons per meter squared times the area of 48 divided by 10 to the 6, and that's in meters squared. Cool thing. Just throw it into your calculator, who cares, but you got that. Anytime you're working with megapascals and millimeters, 48 millimeters squared, that you got 2 10s to the 6 to cancel out. So you get 500 times 48, and right off the bat you get a yield force, or a force max, of 24,000 pounds. Okay, and that was for one rope. You know what I mean? And then you could just do it for both ropes. So you could go force max is equal to that same thing times 2 times the area. Obviously, it's just going to double it up. So you're going to get 48,000 pounds. Now, that's the easy and obvious one. That's the kind of the first rule of material mechanics. You put a scale on it. You know, everyone loves that. You know, you get the force meters and you pull steel apart till it breaks. But there's another way to measure, you know, kind of when crap hits the fan, and it's based on change in length. And it's not super intuitive, because if you pull on something until it breaks, you can write down that number. But then if you pull on something, it will change in length. But the change in length that we're worried about, or we're most interested in, is the elastic change in length. So it's a point where if we pull a 1 meter piece of steel 2 millimeters, we can let go of the force and every molecule goes back to its original position. But pull it more, if this starts pulling more than 2 millimeters, it's going to pull like Play-Doh and break. So this 2 millimeters, you know, kind of mentally is a high end. So let's see if we have enough to actually to get what we want. So, you know, this is a parameter of the material. This is what you put a subscript on. So we're going to say, hey, strain is equal to change in length, yield divided by L. But what do we want to find? You know, I just want actual tangible numbers. I want to know the change in length. So now we have to relate it to, we have to use this equation that says, hey, I know what this is. This strain is equal to strength over E. You know what I mean? This typical equations won't give you this strain value, and it's kind of a bummer. You know what I mean? They just won't, you know, just spoon feed it to you. You have to like do some work to get it, or you can just bypass it by throwing in this is going to be strength over area. So now I can solve for this, bring the L upstairs, and I can go change in length yield is equal to strength yield length divided by E. So now I can just write all these in. and I get 500 times 10 to the 6 newtons per meter squared times a length of 40 meters for the problem, divided by that modulus of elasticity, 160 times 10 to the 9 newtons per meter squared. I always change things from pascals to newton meters squared. It just makes your units make sense and cancel. This is a force per, this is like a PSI, it's a force per unit area, and now we're left with meters, so an obvious change in length. So let's do that. 500 times 10 to the 6 times 40 divided by 160 times 10 to the 9. And we get 0.125 meters. Cool. An actual number that, multiply by 1,000, we get 125 millimeters. So this says for one rope, and we're just taking one rope at a time, maybe that's not so obvious. No, there is no... the change in length is a very fascinating one, because it says, hey, if you just have an object that's this long and you change its length by 125 millimeters, then it's going to reach its max. So that's what that is. And then you can go back and take this change in length of 1. So, out of these three equations, if you rearrange, if you throw in... So here's your equation that relates what you, the weight to what you measure in change in length. And so we're going to say F over A is equal to E change in length over L. Now you can rearrange these to get a bunch. I do that in the later part of this video, how I end it. But now we can rearrange for force, and we can say force is change in length EA divided by L. And we already know the change in length, so we can say force is 0.125 meters times E, which is 160 times 10 to the 9. A is 48 divided by 10 to the 6, and then length is 40. And so we can throw that 0.125 times 160 times 10 to the 9, 48 divided by 10 to the 6, and then divide by 40. And guess what? We get 24,000 pounds. You know what I mean? So there you go. So we took that formula, we figured out change in length. Those are synonymous. Like the max change in length is synonymous with the max force. Now how do we get it for both cables? Well, we say force is equal to change in length, EA divided by L. But now we're going to have two of them. So we're going to have, the area is going to be double. So that's all. You have two cables, and then it just doubles it. So you'd have 48,000 pounds. But yeah. So, and I guess that's it. You know what I mean? That was at least within 10 minutes of just using these two equations, throwing it at the problem, and being like, oh yeah, so I can actually figure out, because I solved this and I didn't use this. I didn't say max strength is force over area, and just rearrange and find that force of yield. You know what I mean? Force of yield is the yield stress times the area. And I could have done that right off the bat and done it for one rope or 2 times the area and done it for 2 ropes. And then get that. I just chose to do this problem based on change in length, because there's 100 millimeters of slack, and so I'm only going to change the length of the first rope by 100 millimeters. And then so, hell yeah, I just used this equation. Force is equal to change in length EA divided by L, and I say I'm only going to go 0.1 meters. Throw everything else in, and I get just a slightly lower force of 19,200. I think. And oh hell, I'm sorry. This is in newtons. We're all in metric. I mean, my apologies. Living in the States. But there you go. So so that's how So when I actually solved the problem in my other video, I just used change in length. And you can do that because you got 2 ways to solve a problem. That's all I'm getting at is, and typically what happens is you'll just use this. You'll just use the strength and force and area equation, but you'll totally forget about stretch. You know what I mean? Where they're 2 basically identical functions of materials that have, based on these graphs, whether you say this is force All right, we got to wrap it up. But whether you say this graph is force times change in length, which then your slope is k, you know what I mean, and then your k is EA over L, and so you should be able to spit that one out because the force of a spring is k change in length. And then we know that, you know what I mean, change in length is FL over EA, and then you can rearrange, get force on one side. Force is EA divided by L, change in length. You know what I mean? So just being able to do that real fast is very helpful. And just at the end of the day, this is like, whoa, yeah, I know how many pounds I'm going to put on something, and then I can measure the change in length in inches, you know, with calipers maybe. And so this graph makes way more just intuitive sense than stress, strain. But like I said, this is force over area, and this is change in length over length. And these are you know, you still have to throw in a specimen into the machine and then tug on it. And when you do, you set the area, you set the length, and what you're trying to find is a universal principle of steel that isn't a function. You know what I mean? That works for, you know, so if I put a specimen that looks like that, and then I go out and build, you know, something that's real big, it's going to have the same properties. This is in PSI, so every molecule in this chunk of steel, when you try to rip it apart, can only take a PSI of 58,000 pounds. You know what I mean? And it's kind of cool with steel because even if you compress steel, it'll still break and do bad things at the same 58,000 pounds per square inch. All right, so that's it. I obviously did this video in reverse, so now I'm going to let you guys see how I started. But yeah, I go over 10 minutes of these equations and then put subscripts on. It's very helpful to get used to it. That's what this video is like when it comes down to it. The core of mechanical engineering is like these three equations, how you have, you know, when you throw them together, you have an equation with 5 variables. And then 2 of the variables, whether it's force over area, is its own term, strength, and change in length over length is its own term, strain. Okay, so I'm going to end the video with that, and hopefully this whole thing isn't garbage and is good to go. Alright, thanks for joining me, and guess what? You got 20 more minutes of video. Alright, hell yeah, we got mechanical engineering, and what we're going to do is make mechanical engineering simpler. You know what I mean? No one does that. And this is a 2-star problem. We've already solved it, but we're not technically going to solve it again. What we're going to do is something that I could have done right off the bat, is how to make things super simple, get an answer right away. And it comes down to the equations that I have myself right, and I have everyone right or whatever. So we have strength is equal to force over area. I call this strength, and it's not. It's called stress, you know what I mean? But if you think about it as strength, because the value for steel, you know what I mean, you have a tensile strength, you know what I mean, and that's going to be like 58,000 pounds per square inch. You know what I mean? But that's kind of not true. You know what I mean? Because you have a high end. You know what I mean? You kind of have a breaking strength, so you could do sigma break, or you could do sigma max. Oh, and I'm going to lose my mind if I don't have a pen that actually works. Okay, so there you go. And then the subscript on this would be the most tensile force that you could have per area. This would be your braking force per area, and this would be, hey, your max force for area. So that's one way kind of to simplify problems, is like, whoa, you can put subscripts, because in general what you want to do is know that a material has kind of a high end and a breaking point, you know what I mean? The tensile strength, that's typically, oh, and then this could also be yield, you know what I mean? So the tensile strength could just be where it yields and starts to turn into plastic. You can get a little bit more juice out of it, but this would probably be 58,000 pounds per inch squared. And that brings up kind of what we're doing in this problem, is that it's a elastoplastic problem. So when your strength, or let's say stress, gets up to this 58,000, you can't get any more. And so right here is your change in length, and right here is, let's say, your force. It's not, because this is your change in length divided by length, and this is your force divided by area. So this graph is always your stress and strain. Stress and strain graph. And so that's what we're going to talk about, because I think that gets confusing for students, where it's just like, well, at the end of the day, you're basically wanting to know what the force is and the change in length. And so let's take a step back, because I really wanted to get to just those simple perspectives. So this is, material mechanics kind of a two-way street. There's two ways to figure out when something's going to break. At the end of the day, that's kind of what we want. We kind of want to know one way when things break. And so the other way is we know that things stretch out, and we're going to say, I'm going to call this stretch, even though it's strain. So let me write what I call these. I call this strength, and I call this stretch. And it just makes your mind not melt, and just puts some very common language, that's relatable. And so that's going to be change in length over length. And then the same thing. You could have the, and yeah, this is a good place to, you could have the max tensile strain. You know what I mean? That's going to be your change in length, your tensile change in, your change in length due to that tensile strain divided by length. Now, what the hell are we talking about? So if we have like a 1-inch steel bar that's 1 meter long, for steel, we can put a load on it of 58,000. That's kind of the max load, let's say, 58,000 pounds over an area of 1 inch. And guess what? It's gonna elongate. And we can visually maybe see that elongation or measure it. It's only going to be 2 millimeters, so that might be very difficult to see. But and at that point, crap's not going to break right away, but it hits this point where going unchecked, and that starts to move. You got up to 60,000 pounds. Well, this might now just move with, just constantly move. You know what I mean? So if this is 58,000 and this is in psi, because this is in psi and this is dimensionless. That's the part. The fact that this is in psi and not pounds, and the fact that this is dimensionless and not in a dimension, makes material mechanics kind of just difficult to get this grasp. To get the grasp that, hey, you have like a max force and then a max change in length. And the second that you observe this 2 millimeters change in length and then put more force on it, well, the thing's just going to change in length until it breaks. And if you're not super cautious about the moment that you made it elongate more than 2 millimeters, but then caught it before it elongated, let's say 5%, because this 2 millimeters of 1,000 millimeters, I mean, if you do a ratio between 2 to 1,000, and I think that is visually, obvious, but this gets you 0.002, and written like this, it just, for most probably students, is just a nonsense number. You know what I mean? That's why I always take this number, 0.002 times 100%, and then you're like, oh, okay, so that's going to be 0.2%. So if I know the length, 0.2% of the length is going to be kind of my max change in length before it turns into plastic and people lose their lives. You know what I mean? So, but for some problems, it's okay to hit this plastic region to here as long as you got something else backing it up, like another rope. Okay, so why are those two things easy? That's kind of what I wanted to get at. So we're going to grab a new sheet of paper. So we have strength is force over area, and then strain is, and I'll just say stress. So stress is force over area, and strain is change in length over length. And we got two different things we can calculate right off the bat. So for this problem, it gives us steel cables that are 40 feet long. Okay, so we got a length, and it gives us the area of the steel cable, so we got an area. And then it says, hey, you know how we have like, hey, braking strength or yield strength or tensile strength? Well, this gives you the yield strength. Cool, so we already have yield strength of 500 megapascals, which is 500 times 10 to the 6 pascals, which is 500 times 10 to the 6 newtons per meter squared. All right, cool. So we know area and we know that number. Cool. And then technically we do know this. So how do we technically know that number? Well, because we know that there is a relationship between these two equations. Because we can pull on our 1-inch piece of steel until we put a force of 58,000 pounds, or measure a length of 2 millimeters, those two things are synonymous. So we can basically have an equation that says 58,000 pounds is equal to 2 millimeters. Now, and this would be like force is equal to change in length. You know what I mean? But obviously 58,000, the number 58,000 isn't equal to the number 2. So you're going to have something like this. Force is equal to K, change in length. Now this is the first thing that you should probably learn before the equation I'm going to write, because they don't do it that way. They do the stress-strain graph where they're saying force divided by area is equal to change in length divided by the length. Because they actually, in a machine, put a specimen, they know the area, and they know the length. But what they want to do is, the reason they do it this way is because they want to give you numbers that are universal for any shape. You know what I mean? Because this you had to choose a length and you had to choose an area. We got to get some more time on the clock. All right, hell yeah. So, but it would be nice if you're just like, well, I just want to do a graph that says, hey, if I have a force of 58,000 pounds, what's my change in length? So I want to do the same thing right here and say 2 millimeters and then a force of 58,000. And it's the same. It looks the same. 58,000 pounds and 2 millimeters. This would be 0.002, that 0.2% of total length, and this would be 58,000 pounds. And it's just convenient because our area was we just chose a area of 1 inches squared. Alright, hell yeah. And right here you should be able to see that this is just the force of a spring. But in general, you have a force that is proportional to change in length, and you have this linear line, so we know that it's a linear proportion, so then you can just go forces is K, change in length. Alright, hell yeah. And I feel like I'm doing a poor job because what I wanted to do was just instantly throw these two equations at the problem to get 2 answers. Like that's kind of where we're going. But you do have to introduce this third equation that says what they do is say that strength is equal to strain times modulus of elasticity. This is the same thing here that we just did. It's basically saying, and so this isn't a very good way to write it. You should be writing it like this, is that strength is equal to E times strain, because now we have, here's the constant, and it's basically saying strength, or we'll just say how it is. It's called stress is equal to, a proportion of strain. So now we can write in the 2 numbers. We can say for normal steel, you get 58,000 pounds per inch squared. That's in psi, and that's going to be proportion. That's going to be equal to 0.002. So if we observe a change in length divided by length, so that's what strain is. If we observe 0.002, and that's, when we pull something in a machine, that's what we're observing. And once we observe that, like, hey, that's going to be synonymous with its yield stress. So we have yield stress, and I guess you would just call this yield strain, because you do have subscripts. So I think that's useful. So we have, so let's write the equations again. Force over area, and then strain is change in length over length. And then we have stress is equal to, and I will put the E in front just because it makes more sense. It's the constant, and then times strain. And so now if we want to know strain, let's say we wanted to know yield strain. So we're going to put some little values on this, and then we're going to rearrange the equation, bring the E downstairs. So now we get modulus of elasticity divided by the yield stress. Yeah, see just how using the correct verbiage it just makes your mind melt. But anyway, so right there, there you go. So now we can find the yield strain just by values that we already know. And so we can rearrange this equation. Or what are we going to do? Oh, yeah. But again, like I said, this sometimes just visually isn't going to give you, it's going to be a small number that you're just going to not care about. And so that's kind of frustrating. This strain is like 0.002, where if we're working in metric, maybe we can get something that's like 2 millimeters. So then what we want is we want to know that stretch is change in length over length, and we want to throw that in. And we can still put this is like, hey, how it was made, but we can put a subscript on this, the yield change in length. So let's do that. So we're going to go change in length yield divided by length is equal to E divided by yield strength. Cool. Now we can just rearrange, because we do want to find something tangible. That was the whole point of this. So we have change in length yield is equal to EL divided by yield strength. So there you go. So this is the first equation that I would throw at it, and then obviously this was the easy one. It gave me yield, the yield strength, and I'm just going to find the force to yield. So we're going to rearrange this equation for force, and we got force to yield is equal to the yield strength times area. And now that was it. Even though I made that hella complicated, at the end of the day, you can like that's why, like, I just, if you're the first time you do a material mechanics problem, you want to get all these equations on paper. F over A. You want to get strength is change in length over length. Then you want to get the ratio between them, and I guess I will start doing this EE this way, because this is your constant, your constant. So then you can throw these in. So I would just do that. F over A is equal to the constant, and then throw this in for E, change in length over length, and then you can rearrange to whatever the hell you want. If you want to find change in length, get the E downstairs, the L upstairs. That's going to be the easiest one, and it's FL over EA. It's very symmetric looking. EA is always going to be together as a package like this. FLEA, maybe spells fleet, whatever. But then you want to maybe find the force, you know what I mean? So force, maybe force max is equal to change in length, bring the EA upstairs. EA divided by L. And then you might want to make this look like a spring. So the force of a spring is K change in length. Well, we can bring the change in length over there and just say force is EA divided by L change in length. So now we know that the spring constant of any material is EA divided by L. Cool. And you can use this formula. And that's about it, you know what I mean? And then you can rearrange however the hell you want. And you can get other stuff back. You can see that this is F over EA. So then, I mean, I don't do this. I should do it more. But I can say, hey, change in length is strength length divided by E. You know what I mean? So I see that one. And then, you know, what else could I do? I could see that this is change in length divided by length. So I could say force is equal to stretch times EA. You know what I mean? Force is equal to strain times EA. And I don't pump out every equation, but since you have 5 variables here, you have a lot of combinations, and I always kind of slip on doing these ones. You know what I mean? So even just this, could I if this is all 5 variables, could I get this equation? Well, yeah, let's see. Maybe I messed up on this one. Actually, yeah, I hella messed up. This is good because even just visually I can see this is a mistake. Because E is a huge number, and then divided by a normal number is going to give me a pretty damn big number. And so these are flip-flopped. So let's see where I made this mistake. I said, let's see if this is true. Yep, this is true, and we were trying to solve for this, so I had to bring the E downstairs. Yeah, so that was a good catch. So we have yield, strength upstairs, E downstairs. Cool. And now I can see that if I want to get this, I'm going to have change in length over length. That's going to be my strain. I have to get E to the downstairs over there, and then A to the downstairs over there. And I'll have F over A, so I'm going to have strength divided by E. You know what I mean? So all these combinations you can get. Okay, so none of my videos are fast, but maybe what I'll do is put what the hell I want to do in the next 5 minutes at the front of this video. So that's probably how I will do it. Because that was the whole point of just like going up to a problem and just doing it, you know, just getting some numbers on it real fast. So that's what I'm gonna do this video in reverse order, and hopefully it's appreciated.